So what we have is the first integral. So let's look at the first one. We have the integral of the inverse cosine of x over the inverse sine of x dx. So the first thing we do is we see that's the cosine over sine, and these -1 powers cancel out. So this is just the integral of the cotangent of x dx, and that's also a pretty standard. Oh wait, that is actually all wrong, because these are inverse functions. We cannot actually do any of that stuff. So what we actually will have to do here is we'll have to use an identity. So what we know is that the inverse sine of x plus the inverse cosine of x is equal to pi over 2, because they're complementary functions. So that means that the sine of x is the same thing as the cosine of pi over 2 minus x. And then that means that when you add the inverses together, the cofunctions, you'll get pi over 2. So what we can do here is we can solve for the inverse cosine of x by subtracting the inverse sine of x on both sides. And we see that the inverse cosine of x is the same thing as pi over 2 minus the inverse sine of x. So what we can do is we can actually replace our numerator with that exactly. So what we do is we have the integral of pi over 2 minus the inverse sine of x over the inverse sine of x dx, and what we see is that we can actually split the fraction, and integrals are linear operations, so we can also split the integrals. So this would be one of our integrals, and this would be one of our other ones. So let's do that. So we have the integral of pi over 2 over the inverse sine of x dx minus the integral of, and then the inverse sine of x over the inverse sine of x, that is just 1. So we then have the integral of 1 dx. So we know how to solve this. So that's pretty easy. So let's look at the first one. How do we do that? Well, first thing we can do, we can take the pi over 2 constant out. That's pi over 2. So this is just going to be focusing on this integral, because we know that this part right here is going to evaluate to x. So this is going to be pi over 2 times the integral of 1 over the inverse sine of x dx, which is a pretty cool integral on its own. And what we can do is we can try taking a u substitution. So we can say u is the inverse sine of x. Therefore, the sine of u, because taking the sine on both sides, the sine of the inverse sine of x, they will cancel out. You'll just be left with the input, which is x. And of course, that is bounded because bounded by negative pi over 2 to pi over 2. So, but this is an indefinite integral, so we don't need to worry about that. So we have the sine of u being equal to x. Therefore, dx is going to be the cosine of u du. And that looks fine so far. So we have now pi over 2 times the integral of 1 over, and then the inverse sine of x is our u, and our dx is cosine u du. And this is actually a very famous special integral. The integral of the cosine of u over u is just the ci of u. This is a special function that is, of course, non-elementary, which is why we had to create special notation for it. So what we actually have here is pi over 2 times the ci of u, because remember, u is our input right now. And what is u? Well, u is the inverse sine of x. So we can write the final integral here. We have the integral of the inverse cosine of x over the inverse sine of x dx. Well, that's just going to be equal to pi over 2 times the ci of u, which is the inverse sine of x, and then minus, and then the integral of 1, of course, was x. So we can put a plus c here, and that is the first integral. So now let's look at the second one, the second integral. So the second integral we have is the integral of the square root of the inverse cosine of x, which is a pretty scary looking integral. But it's not so bad once we see that we can take a u substitution and set that actually equal to the whole thing. So u is the square root of what is happening. We have the square root of the inverse cosine of x. And with these, it's always a good idea, if it looks simple, to solve for x. So we can actually solve for x fairly easily here, because we square both sides. We get u squared is the inverse cosine of x. And then we see that finally that taking the cosine on both sides, it will be left with x. Therefore, x is going to be the cosine of u squared. And some of you may already be able to see where this is going. We have the cosine of u squared there. So now what we can do is we can take this to the u world. So this is the integral, and then we have a u. So we have our u, and then our, we have to take dx. So dx is, of course, going to be now negative sine of u squared times the derivative of the inside because of the chain rule, which is 2u. And then du, because of the chain rule once again, because u is a function of x. So multiply by du. And then finally, we have now the integral of u, like so. U times 2u times the inverse, or times the sine of u squared, and du. So what we see here is that we could actually use integration by parts, because this integral sine of u squared on its own cannot be done with elementary functions. However, when we have a 2u here, we see that that is very conveniently the derivative of the inside of this function. So what we can actually do is we can use the di setup, say that we're differentiating now u. This is, of course, plus, minus, plus. Differentiating u, we get 1. Differentiating 1, you get 0. And then integrating, we can actually integrate 2u times the sine of u squared pretty easily, because if we here take a w to be x, w to be u squared, we'll see that dw is going to be equal to 2u du, and therefore du is going to be dw by 2u, and 2u will very nicely cancel with exactly what we have here. We'll just be integrating the sine of w in the w world, which is going to be the negative cosine of w, which is u squared. So what we can do now is we see that this, taking the integral of that, is just going to be, so we don't actually need this, we don't need this row anymore, and the integral of this is just going to be negative cosine of u squared. So what do we do here? Well, we use the integration by parts, so it's uv minus the integral of v du, but in the di setup, you multiply the diagonals together. And what we see here is that we get now negative u cosine of u squared. And then we see that we have negative u times the equation plus the integral, because now we multiply this, so this right here, what we see here, this part here is actually an integral of its own, because we still have to evaluate that. We don't have the, if we had the integral of negative cosine of u squared, then we would just be able to multiply the diagonals once again, but that is exactly what we're doing here. So going back to this, we see that we now have to just integrate cosine of u squared in the u world. And that is a very nice integral, and that is actually the Fresnel integral. Or Fresnel integral. So this right here, just to make a note, is equal to the square root of pi, big square root of pi over 2 times the c of square root of 2 over square root of 2 over pi times x. So what we see here is that we are just left with negative u cosine of u squared plus this integral, which evaluates 2, and then well, this should be fine, yeah. So we just have the square root of pi over 2 times the c of the square root of 2 over pi x. But this is actually not an x, this is a u here still, so this of course still is a u, we're in the u world. So we actually now just have to get back to the x world, because yeah, so what we see here, this is equal to negative u. Well, what is our u? U is the square root of cosine inverse of cosine of x, so negative the square root of inverse cosine of x. And cosine of u squared is exactly x, because we see that cosine of u squared is what we've calculated to be x here. So what we can see, this is negative x times the square root of the inverse cosine of x plus the square root of pi over 2 times the c, the Fresnel integral with cosine of the square root of 2 over pi, square root of 2 over pi. And our u, of course, is the square root of the inverse cosine of x. So the square root of the inverse cosine of x. And here we can put a plus c because we are done, and this is our answer. This is pretty cool. This is a very long but very interesting integral utilizing the Fresnel special integral. And finally, looking at the third integral that we have for today, and that is going to be the integral of 1 over the inverse cosine of x. Well, that is very similar to what we've done in the first question, so we'll actually be looking at that squared dx. So how do we go about this? Well, what we can do, we can just try taking another u substitution. So we say taking u to be the entire denominator now will not be so nice because we have a square. So then you would have to have a squared, which makes it more complicated. So we take a u to be equal to just the inverse cosine of x once again, and you see that the cosine of u is x, which means that dx is negative sine u du. So what we can now see is that taking this to the u world, we have the integral of 1 over, and then cosine inverse of x is our u, but we still have the squared, and our dx is negative sine of u du, so we take the negative out here and we just have sine u du. So what do we do here? We have the integral of sine u over u squared. So let's just write this here. So this is equal to negative the integral of sine u over u squared du. However, what we can actually see is that this u squared can be written as u times u, and we have the sine of u over u times u, which you can actually write as sine of u times 1 over u du, because this evaluates to the same thing. And here we will see that, or wait a second, that does not actually help us much because that's going to lead with a natural log. So what we'll actually do is we'll separate this entire thing and say that this is the sine of u times 1 over u squared. That will, of course, evaluate to the same thing. So what we can do here, we have a product of two functions, so let's just take an integration by parts. So we have the d, let's just do it here. We have the d, so we're differentiating the sine of u, and we'll see why we do that, because taking the derivative, that's going to be the cosine of u, this is a plus minus, and integrating now 1 over u squared in the u world, of course, that's going to lead us with, so that's the integral of u to the negative 2, add on to the power, divide by the new power, negative 1 over u, we get here. So now we take the product of the diagonals, and then we take this to be an integral. So let's continue our work here. So let's just see now, this is it's equal to negative times, and then let's just put a big bracket around here. We have the product of the diagonals, which is negative sine u over u, and we subtract now the integral of this row right here, the integral of, but then actually wait, that was a joke, because what we see here, if we just make this more clear, this is a subtraction already, and we have a negative sign here. So what this actually becomes is this actually becomes a plus the integral of cosine u over u du, of course. And just we have to be careful of our negative sign, so let's just double check. So what we did, we took the product of this diagonal, which is negative sine u over u, and remember we still have this negative factor out of everything, and then we're taking this to be an integral, which is the negative and the negative make a positive, so we have the cosine of u over u. And yes, we looked at that earlier, or something similar. That is just the ci of u. So this, and now let's actually distribute the negative to each term here. We see that we finally get, or not finally yet, but we have the sine of u, because this negative and this negative cancel out. We have the sine of u over u minus, because this negative gets distributed, the integral of cosine u over u is the ci of u. However, we are not done yet, because we still have to take this back to the x world. So we can finally say that this is going to be equal to the sine of u, which is actually, u is the inverse cosine of x here, which is what we made, and this is not a w, this is a u, and that is the sine of the inverse cosine of x, and then over u. And what is our u? Our u is the inverse cosine of x. So we have the inverse cosine of x here. And then we subtract the ci of u, which is the inverse cosine of x. And we can actually do one final bit of simplification over here. And what we see is that we have the sine of the inverse cosine of x. And that can actually be simplified, because we can draw a triangle. We have the inverse cosine of x. So that means that we must have some side lengths. We have some information about side lengths. We know that the cosine is the adjacent of the hypotenuse, which must be x. So this must be x over 1. This must be the square root of 1 minus x squared. And now, taking the sine of that angle, that is opposite over hypotenuse, which is this over this. So the sine of the inverse cosine, so let's just write this here. We know that sine of this angle right here, we get the square root of 1 minus x squared over 1, which of course can just evaluate to the square root of 1 minus x squared. So therefore we see that the sine of the inverse cosine of x is equal to the square root of 1 minus x squared. So what we can do is we can actually replace that with exactly what we have here. So what we can see here is that this is now finally the square root of 1 minus x squared over the inverse cosine of x minus the ci of the inverse cosine of x plus c. So that is our answer to this integral. And I hope you enjoyed this video where we went through a journey of looking at 3 special integrals. I guess you could say moving up in increasingly in difficulty, although you could say the second question was also quite difficult. So that was it for today's video. I hope you learned a lot more about special functions, and thank you for watching.